Hi class, we are now starting chapter 12, acids and bases. So think about the term acidic, and you may picture powerfully corrosive materials that disintegrate clothes, skin, and even metal. On the other hand, people often describe foods like soda, oranges, and barbecue sauce as acidic. So what's the difference between the nightmarishly corrosive materials and the harmless flavorings of common foods? As we will see in the coming lessons, the behavior of an acid depends on two factors, its strength and its concentration. We will carefully examine both of these. So bases are essentially the opposite of acids. Like acids, bases can be very strong, like drain cleaner, or much more mild, like baking soda. Many household products have acidic and basic properties. Bases and acids neutralize each other, negating their powerful corrosive properties and producing water and simple ionic compounds. In this chapter, we're going to explore the chemical properties of acids and bases and describe them in terms of their strength and concentration. We'll look at reactions of acids and bases and how we can use neutralization reactions to analyze them in the laboratory. We'll begin to see that acid and bases behavior is all around us in everything that we pretty much drink, touch, and breath and fiber of our bodies. Okay, so let's take a look here. So let's begin with the classic definition for acids and bases. This is called the Arrhenius definition. Acids are compounds that produce an H+, which is called a proton or a hydrogen ion. I tend to call it a proton, though your book doesn't. In most acids, a hydrogen atom is bonded to the strongly electronegative element, like oxygen or one of the halogens. In aqueous solution, these compounds ionize to produce an H+, which is a proton, or H hydrogen cation, and a corresponding anion. So for example, hydrochloric acid ionizes to form H+ and a chloride ion. So you can see here. So ionize is simply a fancy word that they become ions. They disassociate from each other and they become ions. Bases are compounds that produce hydroxide ions in water. So hydroxide is right here. Metal hydroxide bases are ionic compounds that disassociate in water to form a metal cation and a hydroxide ion. Potassium hydroxide is an example of a metal hydroxide base. So you can see the same thing happens over here. This is, a polyatomic ion, so it stays together. And here we have just the monatomic ion, which is potassium. In an aqueous solution, the hydrogen ion, cation, is stabilized by water molecules. We can represent this in two ways. Sometimes we show the proton as an unattached cation, or cation with strong forces of attraction to several water molecules. We can write this reaction as HCl, and let me see if it shows on the next page. Oh, here. See, so it goes by itself. So if this breaks up, you can see the H is now attached to a water molecule, and it's now 3 H's and an oxygen. Okay, and then other times we show the proton attached to a water molecule to form H3, which is a hydronium ion. We could also write the dissociation this way. Let me make sure that it's not. Okay. So basically there's two ways to write it. We write it as a proton and it attaches to, so let me see if I can explain this. So basically what this means is that it can be written two ways and they mean the same thing. HCl will dissociate into an H+ and a Cl-. This means the same thing as this. It's just showing in further detail or more specific detail of what's happening. It is a HCl reacts with the water and then it becomes a hydronium ion. But they mean the same thing. So this actually means this. This is more of an abbreviated form, if you will. So if we look back here, that's what you see. We have an H and it attaches here and that's what we see. But so you see the reaction up here. Here we go. So the H here is H+. And basically when we leave it as as we leave it here as an H+, it means the same thing. It's all attached to hydronium ions, but we leave it as an abbreviated form, understanding that means that it's attracted to the other waters. This is just more of a long, not abbreviated in a sense of showing what happens, where you can see that it's actually showing it attached to a water. So we can write it both ways. They mean the same thing. Okay, so now let's look at another example to write an equation showing how nitric acid ionizes in water. Again, acids release protons in aqueous solution. We can show this in two ways. If we don't include water in the equation, then we write it exactly as disassociating. The aqueous indicates that it's in a solution, but it's actually meaning this, that it is attracted to the water, but this is an abbreviated form of what it is happening. So we're not saying the water's not there, we're just not showing the water, if that makes sense. If you do the water in the equation, then you include the water and you show it as a hydronium ion. So again, if you see here, if we leave it as this, we call it a proton. If we leave it as this, it's a hydronium ion. Polyprotic acids can release more than one proton in aqueous solution. For example, sulfuric acid can release 2 protons into solution. Release 1 proton forms the ion, the bisulfate ion, which is what you see here. And the release of the second one, so we take that from here and we start a new one and we leave it here, and the release of the second one forms the sulfate ion. Make sure, sorry, I think I lost my place for a second. Acids can release only 1 proton into solution if they are monoprotic, which pretty much means 1 proton. Hydrochloric acid, hydrobromic acid, and nitric acid are all examples of monoprotic acids. Diprotic acids, such as sulfuric acid, di meaning 2, and carbonic acid can release 2 protons. Triprotic acids, such as phosphoric acid, can release 3 protons. While Arrhenius' description of acids and bases is useful, it's limited to reactions that occur in water. But compounds that behave as acids or bases in water undergo very similar reactions in other solvents. For example, consider these 2 reactions. What do they have in common? In both examples, the HCl molecule transfers the proton to the other species to produce a cation, a hydronium or ammonium, and chloride ion. We describe HCl as an acid in the first reaction, so why not the second? The Arrhenius definition is too narrow. A broader description of acids and bases is the Bronsted-Lowry definition. According to this definition, acids are compounds that donate a proton ion, while bases are compounds that accept that proton ion. So think of throwing a ball. It goes from the pitcher to the catcher. The catcher is taking that ball, so that would be like a proton. That's considered a base. According to the Bronsted-Lowry definition, HCl is the acid in both of these reactions. It donates the proton to the base. Water and ammonia are the bases which receive the proton from the acid. Okay, so now we're looking at 2 different definitions. So the first one was the Arrhenius acid, and the Arrhenius acid was acids that produce protons in water. So that's very similar to the Bronsted-Lowry. It's same thing. However, the definitions with bases are very different. For the Arrhenius, it's bases that produce hydroxide ions in water. And that's not always the case, is that there's a lot of bases that don't have hydroxide. For instance, this bottom one with nitrogen trihydride, this one here is would not be considered an Arrhenius base because it doesn't have hydroxide on it, but it is a base in this definition with Bronsted-Lowry. So that's why the definition had to be expanded, because it was excluding a lot of compounds that were considered bases and did act like bases and had the behavior of bases. Okay, so let's move on. All right, so let's look at an example looking these reactions up with Lewis structures. In the first reaction, 2 electrons from the oxygen reach out and grab the proton. When this happens, the electrons in the HCl bond move to the chlorine atom. The result is a hydronium ion and a chloride ion. In the second reaction, 2 electrons from the nitrogen reach out and grab the proton. When this happens, the electrons in the HCl bond again move to the chlorine atom. The result is an ammonium ion and a chloride ion. In both of these reactions, HCl gives up a proton, so it's an acid. The water and ammonia molecules both receive the proton, so they are the bases. Let's look at another example of a Bronsted-Lowry acid-base reaction. In this reaction, ammonia and water combine in an acid-base reaction. Which behaves as the acid? Which behaves as the base? So if we look here, then we notice that NH3, if we go on the other side, what happens to it? It becomes ammonium. So it forms NH4+. So that means that this one must be the base because on this side it takes that proton. So we denote this as the base. I keep getting lost, I'm sorry. On the other hand, if we look at H2O, we notice that on the other side it forms hydroxide. So water behaves as the acid because it loses the proton. So notice in this reaction, ammonia combines with water to produce a hydroxide ion. Substances that are basic in a Bronsted-Lowry sense, which are proton acceptors, also behave as bases in Arrhenius sense, produce hydroxide in solutions. So this is not necessarily a hydroxide, but it does produce a hydroxide. So this is a base, because if we look at what happens to it on the other side, we're basically trying to figure out where the proton went. And that's where you look on the other side to see what happened to the proton. And from there, you can determine that this is the base because it took the proton, and this is acid because it gives away that proton. So let's look at another example. Identify the acid and the base in this reaction, which it's already saying it, so okay. Notice that as we go from reactants to products, the H2O gains a proton. This means that H2O is the proton acceptor, meaning the base. Similarly, as we go from reactants to products, H2S loses a hydrogen ion and a charge of +1 to become HS-. This means that H2S is the proton donor, also known as the acid. So let's summarize these ideas. We define acids and bases in two ways. According to the Arrhenius definition, acids are compounds that produce a proton in water, or hydronium ions in water, and bases are compounds that produce hydroxide ions in water. But according to the Bronsted-Lowry definition, acids are proton donors, while bases are proton acceptors. So the Bronsted-Lowry is the one that we tend to use more because it's expanded. So try to think of it as a baseball. Look at who's the pitcher, who's throwing the ball, and then you want to look at the catcher, who caught the ball. If you try to consider it with something of a mental image, it might make it easier when you're looking at these. You're basically following the proton, which is the ball, and where did it go? Okay, so again, this is just a little review before we start looking at problems. Again, acids this is the general equation of it, and you can see that it breaks up into a proton and then the anion, and same thing as an actual example with HCl, hydrochloric acid. Here, Arrhenius definition, produce hydroxide ions. Here's a general equation to it. And then when you plug it in with an actual, which is, compound, which is potassium hydroxide. Bronsted-Lowry, compounds that donate proton ions, and bases are that accept that proton. So that's how you look. You have to look at the other side to figure out what's going on. And it's basically, remember, look at the proton, consider it like a ball. Who's got the ball and who loses the ball. And that's going to see what you're going to see on this side after it's happened. Okay, so again, here's just another summary. I'm just putting this over and over because you definitely need to know both definitions. But if you can see, the acids are the same for both. It's the basis definition that's different. Okay, so complete these two equations showing how perchloric acid ionizes in aqueous solution. So you're going to do it in two different ways, which is as a proton and which is a hydronium ion. And you can see here, we just simply, you figure out where to break it up, and then you can, this one is a little bit more expanded, and this one, as you're learning it, is probably a better way. This is more of a shortcut because you got to be able to see what's happening, and this is a better way to do it. Remember, they don't always state this, but let's say a compound has hydrogens in it, and then you have an extra hydrogen over here. they tend to separate the hydrogen that's an acid out of the actual compound because of just this. You can break it apart and it's easy. So let's pretend that this was for hydrogens. So it's H4. Then you have one here. That's usually an indicator that this is the proton that's leaving and it's not actually a part of the compound once they're dissociated. Because it would be real weird to have ClOH5, because then you can't visually see that there's a hydrogen leaving. So that's the tip to help you guys, is that usually the hydrogen is set on its own away from other hydrogens in the actual compound, because those hydrogens, they're not leaving. Label the acid and base in each reaction. So I'm just going to show you the page. It may seem a little hard in the beginning, but once you start doing a lot of them, it becomes second nature. Just like everything you guys have learned up until this point in chemistry. And some of it may be really, really difficult, but after a while you look back and you realize it probably wasn't as difficult as you thought it was. So here is the acid. It's telling you which is the acid, which is the base. And you can label them. If you were writing this out, you would write acid, you would write base. These are really easy if you see the hydroxide, because instantly you know. And the other ones you kind of have to look. So for instance, this is a perfect example of, you see this is NH3, this is H2S. This one could be written as HSH to show that one's leaving and one's staying, but they left it the way that it is written in the compound. And HNO2, you can see that the easiest thing is to look on this side. You can see where it goes, and then you can kind of look briefly here, and you can follow where that proton went. An aqueous solution of hypochlorous acid contains which two dissolved ions? So this is one that you're going to actually have to disassociate it. I did not do that here because I want you guys to get there's enough examples here that you should be able to pull it out. For instance, right here, it shows you. And if you have any problems with this, let me know. I'd be more than happy to help you with it. But by this point, you should be getting somewhat familiar with writing equations, and this will help you even more. So as you can see, if you look at some of these, you can just kind of kick them out. This one's kicked out. This is kicked out. This one might seem a little plausible at first, but that means you're breaking up this whole thing, which isn't happening. And when we're talking about aqueous solution, we're talking about water. So we're talking about water in the sense of that's what this is in. It's not going to be in something else, or it will specifically state it's in something else. So when we're talking about these solutions, it's going to be put the acid here, and then you can see what forms with water. That's why I say these are easier to do than the shortcut ones, because it allows you to see what's happening. Like for instance, it will give you the two reactants, so you won't have to figure out if it's not water. If it's not stating it, then it's defaulted that it's water. So it's really easy to kick most of these out, and the only plausible one is this one, because if this reacts with water, it gives the hydronium, and it's just going to leave this as an ion. And remember to put the charge, because when the proton leaves, it's going to leave a charge on this one. Okay, so in the following reaction, we have water and HCl. So what is this asking? It's asking for, is water the acid and HCl the base? Is water the base and HCl the acid? Is water and HCl both acids and water and HCl both bases? Well, in this case, water is the base, right? Because it took the proton, and it means that HCl is the acid. First of all, HCl is a strong acid, and you'll learn what that is in a couple sections. But it's an acid, and it's a stronger acid than water. Water is actually an acid too. It can, depending on its environment. But in this case, this is a strong acid. This is going to end up being a base just by default, once you understand what I mean by strong acid.